Thanks everyone for joining. My name is Timur, and today we'll be speaking about getting started with the Exabyte platform. Before we start this webinar, let me go over a couple of important points. The goal of this seminar is to help users understand the main concept behind the platform. And this is the first webinar in a monthly recurring series. On the first Friday of each month, we're speaking about getting started. And on third Friday of the month, we speak about advanced topics. Every participant of this webinar should be a registered platform user. And we will be distributing this presentation in a PDF format, so there is no need to take any notes. We will also send a recording of this webinar to everyone as well. If you have any questions at any time, we suggest using the webinar chat to ask questions. And we do encourage this communication because sometimes some of these aspects might not be clear, or you may have some other questions related to the entities that we speak about. So please do ask questions at any time. Here is a brief agenda for today. We will speak about the Exabyte platform and its capabilities first. And then we'll speak a little bit about what's under the hood, the infrastructure of the platform, its capabilities, again, the user interface, things like accounts and service levels. And then we'll proceed to speak in details about each of the entities that the platform supports, like materials, simulation workflows, and calculation jobs. In each of these sessions, we'll have a quick Q&A break. So this will be the time for us to answer any questions. All right, so let's go on and speak about the platform capabilities first. What is the Exabyte platform? It's a digital ecosystem that brings together experts with backgrounds in multiple different scientific fields, which helps people that come from computational background and experimental background and data science background to work together to develop new materials. And we on purpose built it in a way that all these different kinds of people can exchange the information and collaborate using a focal point. And we call this focal point the cloud. It can be a public cloud in our online platform. It can be a private cloud in a private deployment of our platform. But what's important is that it supports multiple different simulation tools. It has a very well-organized data platform associated with all these calculations that can be further used to build any kind of artificial intelligence and machine learning. All right, and security is also an important feature. The way that we start with implementing and organizing the materials R&D is by creating a set of entities that the platform operates with. And these entities include things like materials, simulation workflows, calculation jobs, and materials properties. And then we proceed to define the standards that can hold the information about these entities. And we define them as an open source repository containing JSON schemas that represent the formats in which all of these entities are stored. And then we provide a set of extractors that can take information from the tools that people use today, simulation engines like VASP, Quantum Espresso, LAMMPS, excuse me, or any other file formats, and extract it in a native format and translate it into the format that we support as a standard today. Lastly, the applications allow users to utilize the data formats to create and edit materials information. And we have a couple of examples of JavaScript standalone applications that we use inside our platform as well. Here is the platform as it's added to the open source component. And again, we reuse the open source components inside platform.exabyte.io, accessible to everybody. And these components can be further licensed and deployed in the private scenario too, for the people who feel sensitive about sharing their data. And we start with the computational material sciences as the very well-known scenario to us. But we also support the data science workflows and have on the roadmap support for experimental scientists and their work. In the last two cases, we would have to necessarily add the external elements like the data platform that data scientists work today with. and the laboratory equipment that can provide validation points, validation data points to our data infrastructure to make sure that the work that computational scientists are doing, in fact, represents experiments very well. If we think about the digital materials R&D lifecycle, then we can identify 7 different stages of it. That includes designing materials, designing modeling workflows, provisioning high-performance computing infrastructure, controlling the calculations, collecting the data, and building some sort of data analytics. And the way that we position the platform is that we try to provide all of these steps within one single framework. And I will demonstrate some of them to you right now. First of all, here is an example account page, and you can see there are multiple people that are listed on this account, and there are multiple entities like materials, workflows, and calculation jobs. There is a snapshot of the infrastructure that is available to this account and a little bit about its current state. So when people want to design new materials, they can do that online. Well, here is a quick example for a semiconductor thin film supercell. Another functionality comes from the chemistry domain and nudged elastic band calculations, where we can set up the chemical reaction path. We can code it in at the atomic level. So in this case, we see that the hydrogen atom is moving inside a larger cell, representing a chemical reaction. And once we have the structures, we can set up the calculation workflows that can characterize these material structures. We have a set of workflows that are templated and available for users to select. And each of these workflows, when selected, represents a certain logical flow. As you can see here, for example, we have a relaxation at first, and then we do convergence. And then at the end, we calculate the desired property. So the workflow engine is included into the platform, as well as the computational infrastructure. So we can select to run either on Amazon Web Services or Microsoft Azure, scale to a certain number of cores, computational nodes, all of that is included. And once we're done with the setup, we can execute the simulation and track its progress, as this visual demonstrates. And at the end, when the calculation is done, we get the result in the form of a figure, like the band structure in this case, or the chemical reaction profile for the NAV images that we initially created. So all of this information is stored in a database that can be accessed programmatically through the RESTful API. Most of the time when people repeatedly run these calculations, they have some sort of scripting routines that they prefer. And we support programmatic access to our platform too. So in this demonstration, we use Python to import materials, to create calculation jobs, wait for them to finish, and then assemble a data frame that can be used to build a machine learning model. This is handy when we have a high throughput set of calculations that perhaps running through maybe dozens or hundreds of different material formulations. All right, this is just a quick demonstration. And then another handy tool that we have incorporated into the platform is Jupyter Notebooks. So the data that is produced by simulations can be accessed within the Jupyter runtime. And because they run on the same infrastructure, they have access to the same exact hardware and data. Okay, so Jupyter Notebook can be launched in a similar way as the material simulation jobs. All right. Some of the applications that we support today include things like Quantum Espresso, BAS, Plums, and WChem, GROMACS, VM2K, and others. So that's for the modeling tools. For analysis tools, we support VMD, Xkrystal, Vesta, and we can install other analysis tools that our users would like to use. We also have support for Python and shell scripting at the core, and Jupyter, as I just demonstrated. All of these tools can also be accessed at the command line level. So people who are familiar with the way that works, they can set up batch scripts and then submit those for execution to our resource management system. And they can select some of the environment modules to be used within the batch scripts. So here is a quick demonstration when we open a web terminal. So we navigate to the web platform, select terminal from the right-hand sidebar, and then we can use the command line terminal from the browser. Okay, so I'm done with the first part of this overview. Here is the midway summary. Exabyte.io is really a comprehensive ecosystem for materials and chemicals R&D. And our goal is to transition today's isolated, fragmented approach to the data infrastructure that is ready for data-driven science. Today, we see that we transition from simulations-driven science or theoretical driven science to data-driven science, where we have, sometimes we don't know the underlying equations, but we still can apply artificial intelligence to give us, to see the trends inside the data that we produce. And in most cases, companies that we work with and users that we see today, they lack this infrastructure to be able to use artificial intelligence. And that's where we come in. That is what our platform does for the customer. The goal of the platform is to supercharge the computational sciences. We provide a dedicated environment to organize and accelerate their work and connect it with other organizational units, like people who do data science and cloud infrastructure engineers and such. The platform can be accessed on multiple levels, including infrastructure level for compute only, programmatic level on the RESTful API, and the web interface, of course. All right, now I will proceed to discuss the core parts of the platform. And first, let's look under the hood. If you look, go back to the, to the diagram that represents different components of the infrastructure, and then look at the Exabyte.io's GitHub page, we'll see that some of the elements are represented inside open source GitHub repositories that we have there. For example, the standards are present inside ESSI. We have the applications, Materials Designer is one of the example applications. We have Exaparser as an example extractor. And we have a set of Exabyte API examples implemented as Jupyter notebooks that demonstrate how to work with our RESTful API. If you look a little bit deeper, we'll see that there is a certain pattern that we used. And this pattern includes 3 key entities, or 4 key entities to be precise: materials, workflows, jobs, and properties. And material and workflow have to come together to create a simulation job that can produce a property of interest. So we have a material structure, we have a certain logic inside the workflow, we execute the simulation to produce a characteristic property of this material. Materials can also have non-characteristic descriptive properties that are present before we execute simulations, and those are really associated with material structure, for example, or something that it intrinsically and inherently has before doing any kind of characterization. We separate these entities on purpose to improve the modularity and in order to cover multiple different materials types and simulation types. The entities have a certain kind of data structure that we use to represent them in a database. And this data structures are based on JSON schema format. And they all can be found inside this Exabyte.io ESSI repository. ESSI stands for Exabyte Source of Schemas and Examples. And this repository also is a Python and JavaScript package. So it can be downloaded from pip or from NPM and used in Python or JavaScript projects to validate the data structures that you use internally. So here is an example schema for a material. It contains a certain set of properties defined by JSON keys. For example, it has formula, has lattice and basis. And here is an example of that adheres to the material schema. So this is a material that is stored in a database, and this is a schema that defines the structural representation. So this material represents an FCC silicon in its primitive configuration. And as you can see, there are coordinates, there are elements that are stored inside this data structure, and some additional keys as well. Sometimes when we work with the platform, we want to see the raw data. And that is possible in the case of materials list, for example, by expanding the item. So if we select the actions dropdown and then click on expand, we will see the underlying data structure in raw JSON. Sometimes this is handy because the table itself might not represent all the necessary information, and this is how you can get access to it. So once again, the entities that we encounter inside the Exabyte platform are defined within the Exabyte data convention, or as we call it, SE, and represent JSON schemas with examples side by side. The definitions are meant as a unified format to incorporate multiple different material types and modeling approaches. The platform provides a user interface and alternative access options like remote desktop and RESTful API. For the people who understand the software aspect of it, we encourage them to contribute new functionality, and that can be done by putting a pull request on GitHub. Here is an example pull request. We'll review it, we'll converge on the code, and then incorporate it into our platform. Next, let's speak a little bit about the main user interface components. And here is how the platform looks like for a user, right? There are 5 key components that includes the header at the top, the left-hand sidebar, the right-hand sidebar, the footer, and the support widget in the left bottom corner. And let's go and walk through them one by one. So let's start with the support widget because that's the most important component in the beginning. So when you click on the support widget, it opens up this form where we ask for your name, your email address, and a little explanation of the platform. We encourage people to submit screenshot or screencast of the problem because otherwise it is very difficult for us to understand the nature of it. Sometimes this could be an interactive chat when we have people standing by to answer the questions. And most of the time it will be this form. There is also a chat window present on the right side of the screen, but we discourage the use of it. It's only meant for the people who are not logged in yet to assist with any kind of problems during the registration, during the login process. Next, let's speak about the header. So in the header, we have in the top right left corner, a trigger that can open the left-hand sidebar. Okay, and here we have links to all the entities that are created by this account, including materials, jobs, workflows, and others. So here, once we click on the left-hand sidebar and say materials or projects, we'll get to the account page that allows to further navigate to all of these items. Now, in the top right corner, there is a username and account type. If you click on that, we'll open the right-hand sidebar where we see links to account preferences, billing and payments, and things like remote desktop and command line terminal. There is also information about the infrastructure and the accounts that are available to this user. So we just spoke about the general user interface. There are also specific entity-related interface components, and we identify 3 types of them. First is the Explorer, or a table, a list of items, a list of entities to explore them. And the second component is a Designer. It's an online development environment for the creation, editing, to be able to adjust and modify the entities. And the third component is a Viewer, which is a dedicated page that shows the entities and allows for some small adjustments, like adding metadata, for example. Let's look at the Explorer first. So here is an example, a Materials Explorer. We can see the list of entities that this account has access to. And at the top, we can see the toolbar, the Actions toolbar, and each entity also has a drop-down of the entities that pertain to this specific entry. So the toolbar is at the top, the drop-down is present at each entity. And at the top, we also have a search bar that we can use to filter the items in the list. Next component is the designer. And here again, we have the header menu at the top with specific functionality per menu item, the list of items, the list of materials in this case that are present inside the designer. And then there is a crystallographic panel and a 3D view panel as well. I will go through this in a bit more details in a couple of minutes. And here is an example viewer component where we can see the material, its structure, and some crystallographic information again, and the metadata that we have associated with it. Next, let's speak about accounts and sharing very briefly. Accounts can own and perform actions on the entities. So accounts really define the different ways of how users, humans, can interact with the platform. And accounts have multiple or only one members, depending on the type of them. If that's an organizational or team account, it can have multiple members. And if it's a personal account, by definition, it only has one. Organizational accounts can have different permissions on entities. So based on the teams. So there could be a team that only has read permissions, and there could be teams that have read and edit permissions, and so on. Account members have shared access to entities, and this shared access type is set by the account administrator. We also introduced the entity collection, so the collection of entities that belong to a particular account. And we have the notion of the entity bank. So entities are collected per account, and each account has an independent entity collection. Unique entities in this across different accounts are collected inside a bank, as we call it, using a mapping function. So for example, if there are two accounts that created the same material, and we know that it's the same material based on the structure, then all of them will be pointing to the same entry inside the entity bank. The entity bank entry can be identified by using the exabyte ID property of the entity itself. And depending on the service level for this account, the access could be private or public. So if there is an account with private data, then the entity that it creates, the copy of it inside Materials Bank, nobody else has access to it. And if this account doesn't have private data, then all the other accounts can see the entities in the bank as well. Here is a quick demonstration of how one can access the entity bank. There's a shortcut action in the Actions toolbar. And we recommend using the entities produced by the curators account, because those are the ones that come from the Exabyte team, and we make sure that these entities work well. For example, if you use workflows, we recommend using workflows that are produced by curators. I mentioned the service levels already. So here we can see the comparison service levels define the features that are available to accounts. And we have 4 different kinds of service levels. When users first sign up, they are assigned a free service level with some resources to try the platform, like initial allocation, initial storage quota, and such. And then there is a pro service level that is meant for individuals, and there is a team service level that is meant for team usage, collaborative usage. And then there is also an enterprise service level that is meant for larger teams and enterprises to work together. So some of the features of the service levels are the same across different kinds of them. So the disk space, additional disk space price or price per core hour of compute is the same across all three. But there are also differences, of course, in the number of account members, in the number of projects that are available to each of the service levels, things like private data availability and command line access and such. So let me summarize with the core components here. We define data standards and entities. And the way that we think about this data standards is a unified format that can incorporate multiple different material types and modeling approaches. And we really welcome the contributions from the users to help us cover their particular use cases. We provide the user interface to work with these entities and also alternative access options like remote desktop or REST API. We define a set of accounts that can perform actions on these entities in a shared way. And these accounts have different kinds of service levels, coming from free to the enterprise type access. Okay, I'm done with the first part of it, which is the overview of the Exabyte platform. Now we'll go and speak in details about materials, workflows, and calculation jobs. But before we do that, let me see if there are any questions. Looks like not, okay. Well, let's continue on and speak about materials. So first action that users perform most of the time is to upload the materials that they work with today. And most of the time they come in a certain format like POSCAR or CIF. And here is a quick demonstration of how we can do that. We'll go to the list of materials per account and select the upload action in the actions toolbar, which takes us to the upload dialog. And then we click on select items inside the dialog and select one or more files from disk. In this case, I'm using POSCAR files, the VAST format. So what happens after is that the information is being fed to the upload dialog, where we can review the content of these files. They have to be text files, so we can visualize the in-textual content of it. And then we can associate some metadata like put tags to one or more entries inside this list. For example, in this case, I want to associate tags only with one of these entries. So what I do is I click on the tags inside the toolbar, and then type comma separated values like tag 1, comma tag 2, submit it, and as you can see, there are tags associated with this entry only. Then I select all the entries and click upload action, and 3 materials are being added into my collection, and one of these materials now has 2 tags associated with it. Okay, so that's how we upload materials information. Second option is to import materials from an online database. And in this case, we'll be importing materials from the materials project database. It's a well-known and widely used database of structures and calculations. So here, again, we click on the import action at the top, and then type materials formula, like magnesium dioxide in this case. We see that there are 2 entries, and we can click on these entries to see the detailed information for each one. Or we can select this entry and then click on import action to add it to the account collection. Okay, when the process is finished, we see this green pop-up at the bottom of the screen, and the new entry is added to our collection. So that's how we import a material. As the collection of materials inside the Exabyte materials bank is growing, we have the third option, which is to import material from materials bank. And that can be done by navigating to the bank first. So we open the left-hand sidebar, click on the bank, and select materials there. And just like in the previous video, we filter the materials list using magnesium dioxide formula. and then select this entry and click copy. So in this case, what happens is that the entry from Materials Bank is copied to my account collection. And when I come back to it, I see that entry at the top. All right, so 3 ways to add materials to the account collection, either to upload, to import from an online database, or import from Materials Bank. There is a quick shortcut that users can use to navigate to the bank directly from their collection. And it's shown in this slide. Now, in some cases, we want to use a more advanced search option than just the materials formula. And we support this capability as well. So if we click on the advanced search in the toolbar, we are presented with a query builder, which has multiple queries that are connected with each other through an and an or logical condition. So here, for example, I have a query that is built based on materials formula, the unit cell volume, and tags. So the query that I have just built will filter the materials list to only show materials that contain aluminum inside their formula, that have volume of the unit cell less than 80 angstrom cubed, and materials that have tags that contain high pressure inside them. And I click on search, and I see one material entry. When I reset the query builder, I can see again all the materials in the list. All right, and this query builder provides a very flexible and robust functionality to filter materials according to your liking. Now, I briefly mentioned the designer component. So let's speak about how one can access it. To navigate to the designer, let's click on the Create button that is available in the Actions toolbar for materials. When we do that, we are presented with the Materials Designer interface. And again, it has the header menu at the top with multiple menu options. Here's the items list on the left, which contains material entries that are currently active inside the designer session. And we have the crystallographic data panel in the middle, and the 3D crystal viewer panel to the right. So let's look at an example usage pattern where we import a material from our account collection to further edit it inside this materials designer session. First, we click on header on the input-output menu, and we select import inside the menu. It takes us to the import dialog, and in this case, as the import dialog has it, we are importing materials from our own collection. So again, the way that we designed the platform is that any kind of edits to the material structures are reflected inside the account specific part of the materials collection. So we always work with entities that are owned by the account when we edit them. But before editing, before the account contains any kind of entities, we have to import them or upload them as we just discussed. So here I'm importing a material from the account collection to further edit it inside the materials designer. Okay, and now I have 2 entries on the left, silicon FCC and this MP661. So let's remove the silicon, which is the default entry. And now I have the aluminum nitride as the entity here that I can work with and modify the structure, adjust the crystal lattice, adjust the basis. So do 3D manipulations with the structure inside Materials Designer. I will not focus on how to do that here in the session. Let's do that in the advanced topic seminar coming up in a couple of weeks. Next, let's proceed to the second entity that we discussed, the workflows. And just like with materials, we have a bank, the platform-wide workflows bank, that contains all the unique workflows that users have created. And for someone who just starting with the platform, we think that the best way to start is to import one or more of these workflows. To do that, again, we open the left-hand sidebar, click on bank and then workflows. And we can see the list of all the workflows that are present in the bank. If we want to calculate band structure, then we can search for band structure as in the workflow name or the property that it extracts. And then we select the band structure workflow at the top. Again, in this demonstration, we do not have the creator name in the list, but it can be also shown by clicking on these three dots and selecting creator as one of the fields. And we suggest using the workflows that are created by the curator's account. Okay, when we click on copy, we see that the item is copied to our private collection. And when we navigate back to the list of workflows, we see the copied workflow at the top. The second option, excuse me, is to design a workflow. But in order to understand how to do that, let's first look into the inner structure of the simulation workflows. Since it's a static entity, it is represented by a data structure. We have to understand what constitutes the data structure first. And the workflow contains multiple sub-workflows, as we call them, inside itself. And sub-workflow essentially is a set of distinct units. So sub-workflow is further subdivided into units. And each sub-workflow is specific to a particular simulation engine. For example, if you use VASP, or Quantum Espresso, or LAMMPS, then sub-workflow can only contain a single simulation engine, like VASP. Sub-workflow can contain a single model and method as well. So it's a density functional theory, pseudopotential method, and sub-workflow only can contain one. This concept is really introduced for modularity to be able to use some commonly used simulation logic. Unit is an elementary calculation. It is executed in certain succession based on the logic inside the workflow. And it can represent things like condition, in case we do some sort of a convergence study, or it could represent a MapReduce workflow. Depending on the logic that we include inside sub-workflow, we can have different kinds of units. So units can have the execution as their type. For example, to run a Quantum Espresso calculation, they can be of an assignment type when we assign a variable, or a condition as a type. Execution units can have different executables associated with it, for example, pw.x. And execution units can also have different flavors, like pw.scf, to make this process modular and reusable. So pw.scf unit has a certain input file associated with it, and it also uses pw.x as an executable. So here is the user interface component that represents the workflow designer. And it also has the header menu at the top, where we have the name of this workflow and some metadata associated with it. On the left, we can see the list of sub-workflows and the items list. And on the right, there is a sub-workflow editor. So if we want to edit the number of sub-workflows and add a new one, we can click on this plus button. And a new workflow will be added into the list on the left. And when it's added, it's an empty sub-workflow. We have to go and initiate it with units. I will demonstrate how to do that next. So inside this sub-workflow editor on the right, we also have the actions menu bar at the top. We have the editor tabs that contain the information about the workflow, sub-workflow. And at the bottom, we have the units flowchart that contains the flowchart logic. So if we look in more details at the units flowchart, we'll see that the currently active unit is highlighted in gray, and unit types is shown. Unit type is shown at the bottom of the box. So E means execution. When we click on this item, we can see its content. But before going into that, let's understand how the logic is represented. So this functionality is still under development. So we have the rudimentary representation of the logic in this case. So the real workflow flowchart is shown on the left. It's really a convergence study where we define a variable and then we execute the self-consistent field calculation and then extract its output as a total energy and see whether the total energy is converged. If it's not, we increase the number of K points and pass it back to PWSCF calculation. This workflow presently is represented by this visual. So the workflow on the left and the workflow on the right do exactly the same thing. And A here represents the assignment unit where we set up the n_k variable. C is the condition unit where we check whether the output, which in this case is the total energy, minus the output at the previous step is less than the threshold. And E is the execution unit where we do the calculation itself. Now, when we open the unit, we see that it has certain template content that we actually pass to the calculation. And we have some additional metadata associated with this unit, like its executable, its flavor, the properties that are being extracted, the monitors, like standard output, convergence graph, and certain information associated with where exactly inside the sub workflow this unit sits, like the name of the unit that comes next, name of the unit that comes after it. And in order to understand the templating logic, we have to look at the content of the input template. And we'll see that there are curly braces that represent the variables that this template has inside itself. These variables are being populated based on the metadata that comes from materials. So the way that we render the final content of this input template is based on the material that we associate with this job, right? In the beginning, I said that a job is formed when we have materials information passed and put together with the workflow information. So before there is materials information, we really don't know the final content of this input file. We only have the template. But if we bring the information about the material structure, like the unit cell parameters or the atomic species, we can render the final textual output for this workflow, which contains the materials information as well. And that is what we call the first render. The first render that happens on the web. And as you can notice, there are some variables that are still present even in the rendered text. And that's because really for the user, it doesn't matter which working directory we are going to assign to this job. And when we copy this textual file to the infrastructure, we substitute this job working directory variable at the runtime. So that's what we call the second render that happens during the runtime. And at the end, we pass the fully substituted input file to pw.x to execute this calculation. Right, so that's an important concept to understand, that we have two rendering processes, one on the web and one on the infrastructure. When we do things like convergence studies, for example, the second runtime renderer is also important because we can substitute the parameters inside the input file during the runtime as well. Okay, now let's proceed to discuss the calculation jobs. Before we start, there are a couple of important points. Before we run the jobs, we have to make sure that we have created, imported, or uploaded all the materials that we want to work with. And we did the same with the workflows. So the workflows and materials have to be ready for us to be able to run the jobs. When the accounts are created, we only initiate them with an example workflow and an example material. To be able to populate the collection, one can use materials bank to copy materials from there or to upload materials from disk. The same is true for workflows. We also have to make sure that the account has enough balance to perform the calculations and there's enough disk space for this calculation to be done. Then we can navigate to the desired project, which is a collection of jobs. Usually people want to execute calculations based on a certain project, which can contribute to a publication or a particular kind of collaboration. So project is nothing else but just a collection of jobs. The simplest way to create a job is to select the create job link inside the left-hand sidebar. And that's what I'm going to demonstrate here. And this link will take us to the job designer, which has the header menu at the top again, and the materials tab, workflows tab, and the compute tab. We start with going to the materials tab and selecting materials for this job. We can select multiple, and we can do that by clicking on the dropdown in the header and clicking on select materials and selecting multiple entries inside our account collection. So here I'm selecting 6 materials and clicking on the action at the top. And as you can see, the materials tab now contains 6 materials that I can scroll through to visualize their structure quickly. All right. So what's important to notice here is that we see that formula, keyword formula variable was added to the job name. In the beginning, we didn't have it. At the end, we see it's added. Because we have 6 materials, we add a material formula to the name of the job automatically to make it easy to understand which job corresponds to which material. The second step is to select the workflow. And just like with materials, we can open the dropdown at the top and click on select workflow and select one entry inside the workflows list. Unlike materials, we can only add a single workflow because otherwise it would not be clear which calculation we're actually running. So after selecting a workflow, we can see the logic inside it using the workflow tab. Okay. And then the third step is to set the compute parameters for the job. And here is an example compute setup form. It contains the time limit. It contains the cluster parameters. Like we can select a different cloud infrastructure provider to run these calculations on, the resource management queue, number of cores and nodes. By default, we suggest just using the preset parameters just to try these calculations, and that's what we're going to do in this demonstration. Next, we click on the Save button in the header to save the job, right? And that's how we create a simulation job. A couple of notes about the job creation. It's important to understand that workflows cannot be modified during the job creation, and we did that on purpose to simplify the user interface and to assert the data consistency. Because when we modify the workflows right before execution, we cannot assert the metadata. We don't know really what exact logic is performed inside the workflow. Now, it is possible to edit the input preview directly from the workflow, but we discourage it. We suggest that users first modify workflows and then apply those to materials inside the job designer. Multiple materials can be selected inside the job designer, and there is also a way for jobs to span other jobs and wait for their execution. But this is a topic for the advanced seminar. So once we have created the job, it is now present in the list, and it has the pre-submission status, which is shown in light blue. Now, when we click on the entry and select run, we send it over for submission to the infrastructure. It changes the status to S, which means submitted. And after a little while, it starts running. So its status is being changed to A, orange, which means that it's active. We can navigate into this job, open it, and track its progress. So the currently active unit is shown in orange. We can see the standard output of this job. We can see the convergence graphs associated with it. And as the calculation progresses, the units that are shown in green are finished, and the units that are currently orange are presently running. At the end, when all the units are complete, the job also turns green, and the status is shown as finished. When we navigate into the finished job, excuse me, we can see its results. So they are arranged per unit. So PWRCF had extracted total energy, pressure, Fermi energy, and total force. And band structure, the bands unit extracted the actual band structure plot. If we come back to the top, we can also navigate to the list of files that this calculation produced. And we can preview or download each of these files to disk. All right, so this is a quick demonstration of how we can run a simulation job by combining together workflow and materials.